First of all, we've got a roller coaster ride at an amusement park, and it's going to lift a car of a mass of 700 kilograms to point A at a height of 90 meters above the lowest point on the track. The car starts from rest at point A and rolls with negligible friction down the incline and follows the track around a loop of radius 20 meters. At point B, the highest point on the loop is at a height of 50 meters above the lowest point on the track. I want you to calculate the speed VB of the car at point B and annotate your calculation with a description of your results or your approach. Include a specific justification of why the method you chose is applicable in this situation. So I'm not going to write it out. I'm going to show you how, and I'm going to explain it in words and math to show you how to do this. So first of all, this is an example of conservation of energy. So at the beginning, you have all gravitational potential energy because it's not moving and it's at the top. So at the top, the kinetic energy is 0. It said that it's frictionless, so we're not having any work done. So all of our energy is gravitational potential energy. And then at point B, it's going to have some height. And it's going to be moving. Okay, so just remembering with these bar charts, the idea is that it's a visual representation of how much energy is where. So we're going to have just gravitational potential energy at the beginning, which is M times G, and the starting height was 90. And that's going to be equal to 1/2 times the velocity at point B. Times mass times the velocity at point B squared plus mass times G times the height. Okay, and then I'm going to divide both sides by M. All right, so I put in the numbers and I get 882 is equal to 1/2 mass B squared plus 490. I subtract the 490 from both sides. I get 392 is equal to 1/2 B squared. Multiply that times 2. All right, so the velocity at point B is 28 meters per second. Yeah, that was a really good question. So on the left, it was your top, and on the right, it was at point B. On the figure of the car below, draw and label vectors to represent the forces, not the components, acting on the car when the car is turned upside down at point B. All right, so we have two forces, normal and gravitational force. Okay, so gravitational force is definitely going down. Okay, but now here's my question. Is it going fast enough that it doesn't need to get pushed down by the track? Or does it need to get pushed down by the track because it's going too fast? We have to figure it out. But that's okay, because in part C, we were going to have to figure out the magnitude of all the forces anyways. So we're going to do it now. So we're going to remember, which way do we want to say up is? Probably positive, right? Wait, no. We have to make down positive because that's the center of the circle. Okay, so some of the forces towards the center of the circle, because that has to be the positive direction, is FG. We're going to say plus Fn just because I'm going to guess that Fn is going down. If we get a negative number, then we know that we have to switch the arrow direction. Okay, so that's equal to mass times the acceleration to go towards the center of the circle. So Fg is mg. My normal, we don't know. We need to figure that out. And that's equal to my mass times the acceleration to go in a circle, which is v squared over r. All right, well, we just got our velocity. Our velocity was 28. R is the radius, which is 20. Our mass was 700. Oh, and then this one's 700. So we're going to plug all the numbers in. And so you get a normal force of 20,580. And because it's a positive, that means that we guessed the right direction. Now, what I am going to do though is I'm going to change this normal force because this normal force is way bigger than my gravitational force. And then it says, what is the minimum initial height such that the roller coaster will be able to make it around the loop without anything falling out of the roller coaster? At the point at which nothing falls out of the roller coaster, that is your minimum speed at the top. That happens when you do not need a normal force. So that's going to be when there's only Fg. So I can remember, okay, now the sum of the forces towards the center is just Fg, and that's equal to mass times the acceleration to go towards the center of the circle. I'm going to solve. So I'm going to divide both sides by m. All right, so in order to solve for my velocity, I'm going to put in the radius of the circle. I'm going to put in g. I'm going to cancel out those m's, and I get a velocity of 14. So that means I need to have a velocity of 14 at point B, because that's how fast I need to be going so that stuff does not fall out of the roller coaster. All right, so now I'm going to do this again. I'm going to think about what energy I had at the top and what energy I had at point B. So at the top, my kinetic energy was 0, and I have all gravitational potential energy. At point B, I'm going to have kinetic energy and gravitational potential energy. I don't know which one's bigger, so we're going to just kind of go like that. This one's all the way big. Needs to add up to those two combined. All right, and then I have gravitational potential energy, which is mgh at the beginning, is equal to 1/2 mv squared plus mg times the final height, 50. All right, so g is 9.8. My height at the beginning is what I'm solving for. My velocity at this point I just found was 14. So this is 1/2 times 14 squared plus 9.8 times my 50 at the end. Alrighty, so you get a minimum starting height of 60 meters. And then the very last part, it says, now suppose that friction is not negligible. How could your loop be modified to maintain the same speed at the top of the loop as found in A? You would need to change the starting height. So you start with more gravitational potential energy so that even when you lose some, you still are going the same speed at the top of the loop.